Hello, my name is Mike Taylor. I am an associate professor in the Department of Economics at the University of Nevada, Reno. I'm also a state specialist with University of Nevada Cooperative Extension. So my talk today is part of a panel, Modeling Money and Management in the Humboldt River Basin. So I encourage anybody watching this video to also check out John Benedict and Kip Allender's talks, which are the other two parts of the panel. And if you have any questions after my presentation for me or for any of the other panelists, I encourage you to participate in the live Q&A on Monday, January 25th at 10:10 a.m. So in my talk today, I'm going to present the results from two models. These models were constructed to provide estimates of the economic cost of unanticipated water supply reductions for agricultural producers in the Humboldt River Basin. Before starting with the presentation, I would like to acknowledge, first off, the contributions of my co-authors. This project was started as a collaboration between Dr. Kim Rollins at University of Nevada, Reno and the Division of Water Resources. Dr. Rollins left UNR in September 2019, at which time I took over the project. And since then, it's really been a collaboration between myself and Mr. Jacob Kingsley, so a very capable undergraduate research assistant. I'd also like to acknowledge the role that Mr. Alec Bowman played, who was a very valuable contributor to the project, particularly in its early stages, while he was a master's student in the Department of Economics at UNR. Of course, the report was funded by the Division of Water Resources, and I'd like to kind of acknowledge and thank the numerous stakeholders who met with the project team in its early stages to kind of help us better understand farming and cattle ranching in the Humboldt Basin and improve the realism of our models. In this presentation, I'm going to present the results from two models. One model of a cow-calf ranch and the other model of an alfalfa hay farm. Both operations and both models use surface water for irrigation. The models were built to represent typical cow-calf ranching and alfalfa hay operations in the Humboldt River region. As such, parameters were chosen both through consultation with the published literature, but also in consultation with farmers and ranchers in the region. The models were used to calculate the economic value of an acre-foot of water not received due to an unanticipated supply reduction, such as the supply reductions that might occur due to conflict with groundwater pumping upstream. Let's talk a little bit about the relationship between this work and conjunctive management in the Humboldt River Basin. Initially, when this project started, the idea was that we would provide estimates of the value of water that surface water users do not receive due to interference from groundwater pumping upstream. I encourage you, like I said in the beginning, to listen to John Benedict's presentation as well as Kip Allender's. But several legal and legislative hurdles have made it unlikely that this kind of financially based mitigation approach is going to be implemented, at least in the near term. Alternative approaches have been suggested, including one where groundwater users pay into a mitigation fund. I think irrespective of whether or not kind of a financially based compensation approach goes forward, it's our hope that credible estimates of the economic value of water in the region will help the state engineer create good policy and kind of optimize use of this kind of scarce resource, optimize beneficial use of this scarce resource. Before getting into the model, I would like to give a quick preview of the results. Starting with the cow-calf ranch, what we find is that reduced water deliveries impact ranch profits by increasing the cost of feed, lowering the amount of feed grown on the ranch and forcing the ranch to purchase feed at a higher cost on the open market. The higher cost of feed then forces the ranch to reduce its herd size, which lowers the number of new calf births and as a result lowers future profits from livestock sales. So in this way, An unanticipated reduction in water deliveries not only impacts profits in the year where the reduction is experienced, but also in subsequent years through reduced herd size. The results indicate that the economic value of an acre-foot of water for the cow-calf ranch ranges from $215 per year in normal water years to $290 per year if the unanticipated supply reduction occurs during a drought. For the alfalfa hay farm, we find that reduced water deliveries impacts farm profits, first by preventing the farm from planting cover crop during fallow years, and then for more significant reductions in water deliveries, leading the farm to reduce its acreage of alfalfa hay planted. The economic value of an acre-foot of water for the alfalfa hay farm ranges from $10 for small interruptions, so 5 or 10% normal deliveries that happen during normal water years. These are instances where the model predicts that the reduction in water just causes the operation to stop planting a cover crop, which is relatively not very profitable on a per acre basis. But then for more significant interruptions or interruptions that take place during droughts, you end up having values of acre-foot of water ranging from $100 to $200 for single year interruptions, and over $300 for interruptions that occur over several successive years or occur in later years of a multi-year drought. So the two models that we develop in this study are linear programming models. So linear programming is a kind of mathematical programming technique that's used to obtain the optimal solution to a mathematical model whose objective function and constraints are represented by linear relationships. So the linear programming model that we use in the study were adapted from work by Alan Terrell and his co-authors. Started in 2002, but there's numerous papers that have kind of taken this approach. And the kind of linear programming algorithm that we use in the study is set up to find the management plan that maximizes the ranch or farm's profits while satisfying all of the constraints that we put on production. So, a management plan is going to involve, for example, in the case of a cow-calf ranch, buying and selling cattle for the alfalfa hay operation, how many acres to plant in the year, whether to rip out fields of planted alfalfa, etc. And then there's numerous constraints on production in the model. There's constraints relative to the availability of land, importantly, of course, the availability of water. There's also constraints on, grazing season access to public land allotment, and also to seasonality for these other foods, other sources of forage. Both models are dynamic, so they look at how the kind of ranch or farm management over a 40-year planning horizon. And the dynamics in the model, so the linkages between years, is related to, in the cow-calf ranch, to herd expansion through reproduction, and in the alfalfa hay model through kind of planting and fallowing. As I mentioned earlier, we assume the alfalfa hay farm can plant alfalfa for 6 years, and in the 7th year they have to fallow the field before replanting. So a big advantage of this linear programming approach that we're taking in the study is that it allows us to analyze how the economic value of water depends on kind of the intensity and duration of the unanticipated supply interruptions, as well as the characteristics of the operation. So how the value of an acre-foot of water depends on the size of the public land allotment, the acreage of the operation, the herd size and the composition of the herd at the time the interruption is experienced. So this flexibility in the model allows us, through choosing parameters and model assumptions, to tailor our predictions about the financial costs of a supply interruption to the kind of specific circumstances of different agricultural operations. So the results I'm presenting today are for what we're terming a typical operation, But this kind of flexibility will allow us down the road, and I'll talk about this kind of in our next steps, to really to have the potential to look at how the cost of water not received will vary depending on when that occurs. If an interruption occurs during a drought, occurs for operations in different places in the Humboldt River Basin, and operations that are of different size and that face kind of different constraints in how they're able to adjust to water supply interruptions. Beginning with the cow-calf range, the two most important constraints faced by the cow-calf range model are land availability and water availability. So land availability matters because the ranch has two sources of low-cost forage grown on the ranch. They have forage from their BLM allotment during the period where they're allowed to graze on their public land allotment. They also have low-cost forage that's grown on the ranch in the form of either grazed meadows or through growing meadow hay, both of which are assumed to require irrigation water. In addition to growing forage on the ranch has the option to purchase forage at market prices. In addition to the kind of the sources of forage, there's also restrictions on when the forage is available during the year. These restrictions apply to forage sources grown on the range. So the public land allotment, this is going to be specified in their grazing contract with the Public Land Management Agency. And then in terms of when during the year they're able to use grazed meadows or use aftermath grazing on meadow hay is also restricted. Water availability impacts the cow-calf ranch in the model by reducing the amount of acreage of either grazed meadows or raised meadow hay they can grow on the ranch. So in years where they receive the anticipated reduction in water supply, they grow less forage on the ranch, and that forces them to purchase more forage on the open market, which increases their costs of feeding their herd. The model assumes that both grazed meadows and raised meadow hay require 1.5 acre-feet per acre of irrigated water per year. This table shows some of the assumptions from the cow-calf ranch. We model 4 different sizes of cow-calf ranch. In today's presentation, the results that I'm going to show you are going to focus on the medium-sized ranch. All these, in terms of size, they all scale. So the ranch has access to a public land allotment, also private land, which they can irrigate to grow meadow hay or as grazed meadow, and they have their expected water deliveries. The expected water deliveries are assumed to be equal to their typical water deliveries for the ranch in an average year, given the ranch's portfolio of water rights. So the expected deliveries are going to be less than or equal to the ranch's full duty, and will be more likely to be close to the ranch's full duty for people with more senior water rights. And the kind of range of expected water deliveries that we considered were based on kind of interviews with stakeholders and water managers in the region. This slide shows some more of the assumptions for the cow-calf ranch. In particular, it shows the conversion between the different sources of forage available to the cow-calf ranch into animal unit months, where an animal unit month is defined as the forage necessary to feed 1,000-pound cow and her suckling calf for a month. This table displays the availability of the different forage sources over the course of a year. Purchased alfalfa hay and meadow hay are available year-round, whereas the forage sources grown on the ranch are only available for certain months of the year. This table gives the assumptions about production costs for forage grown on the ranch, and the cost of purchasing forage, so meadow hay and alfalfa hay, on the open market. What's really kind of important to look at on this table is that kind of the final two rows give the additional cost for feeding a herd of a given size if you were forced to substitute forage grown on the ranch with purchased meadow hay or purchased alfalfa hay. So this table shows the feed requirements for the different classes of animals in the model on an animal unit month basis. So the model assumes that forage demand and supply are balanced each month on an AUM basis. Further, the model assumes that calving takes place in the late winter and that calves are weaned upon return to the base property in October. Some of those calves are sold, some are retained and then become yearlings in the second year and then eventually become cows. We assume that all the steer calves are sold. We don't explicitly model bulls in the model. So we assume the costs, we assume a 20-to-1 bull to cow ratio has to be maintained on the ranch, and that the cost of feeding and tending to those bulls are just included in the herd management costs associated with cows in the model. This table displays the assumptions in the model about the costs of livestock, purchasing livestock, their maintenance costs, and also their average weight upon sale and their sale prices. This table displays the basic financial assumptions in the cow-calf ranch model. So this figure presents the present value of ranch profits, which corresponds to kind of the value of the ranch operation, under a range of different scenarios concerning the intensity and duration of these unanticipated water interruptions. So if we look at here, the ranch is valued at over $2.5 million. These supply interruptions will have kind of a significant effect on ranch profits, but not so much so, except for the most extreme cases, to cause the ranch to go out of business. This table displays the results for the cow-calf ranch for the per acre foot value of water. You can see that the per acre foot value of water ranges from about $215 if the unanticipated supply interruption takes place during normal water conditions. And it goes up to about $290 if the unanticipated supply interruption takes place during a drought where the ranch is already receiving 50% of its normal water deliveries. The reason for the big difference in the value of an acre foot of water is in these scenarios where the anticipated reduction takes place on top of an existing drought. The ranch makes more extreme adjustments in its herd size to manage the increased feed costs associated with the loss of water, and those costs then reduce profits in subsequent years. Some of the very high values on this table, for like $400 or $500, $600, these reflect scenarios when it's still the ranch still stays in business, and it's still profitable for the ranch to stay in business. But in order to keep the ranch operating during these extreme shortfall years, the ranch takes on a significant amount of debt. So these high values are not actually related to how water is used on the ranch, but more like the finances of the ranch and our assumptions about the ranch's cash holdings and the interest rate they have to pay on their debt. This table presents the total cost to the cow-calf ranch of an unexpected interruption equaling 10% of its normally expected water deliveries. So in this case, about 188 acre feet. As you can see, the cost ranges from $40,000 to $54,000, and these costs are annually. So if there were multiple years of unexpected water reductions in water deliveries of 10%, you would have to sum horizontally across each one of these columns. This table presents the results for the sensitivity analysis that examines how sensitive the model's predictions for the value of an acre foot of water are to our assumptions about the price of purchased meadow hay. What this table reveals is that the per acre foot value of water depends critically on the purchase price of meadow hay. When water is not received, the ranch is forced to purchase meadow hay in order to maintain its herd. And the more expensive the price of meadow hay, the more valuable, the higher the cost of not receiving the acre foot of water. Now we're going to turn to the alfalfa hay farm model. This model is similar to the cow-calf model. There's two main constraints on production: the amount of available land and the amount of available water. We assume the farm grows two crops, alfalfa hay and winter wheat as a cover crop. Assume that both crops require 3 acre-feet of irrigation water annually. We assume that the farm has enough land so that in years where it receives its expected water delivery, all of its irrigable land gets 3 acre-feet of water per acre per year. In years where the farm receives less than expected delivery, irrigated acreage is constrained by water availability. And the model also assumes the following crop rotation: that alfalfa can be grown on the same plot for 6 years, and in the 7th year, the plot has to either be left fallow or planted with winter wheat as a cover crop. This table shows that, as with the cow-calf ranch, we analyzed 4 different sizes of an alfalfa hay farm. The results I'm going to present in this presentation focus on the medium-sized farm. This table presents several of the assumptions in our alfalfa hay model concerning yield, production costs, and output prices. It's important to look at the last 4 rows of this table, where it shows the profits per acre foot of water received for the alfalfa hay farm. This table displays the financial assumptions for the alfalfa hay farm. This figure displays the model's predicted present value of future profits for the alfalfa hay farm under a range of assumptions about water deliveries, both in terms of the reductions from expected water deliveries and the number of years where those supply reductions occur. One important thing to notice is that the alfalfa hay farm is very profitable. So even for significant supply reductions, the model predicts that the alfalfa hay farm will remain in operation. It's only in these extreme cases that the alfalfa hay farm would shut down due to water interruptions. This table presents the results from our alfalfa hay model. What is kind of the first thing that's clear from this table is that for interruptions, that unanticipated supply reductions that occur during normal water conditions have a very small impact on the farm's profitability. This is because under the assumptions of the model, all that happens is that these supply reductions will stop the farm from irrigating cover crop in fallow years. And the cover crops are assumed to have very low profitability per acre. But as either the size of the interruptions increase or the interruptions take place during existing drought conditions, and these interruptions then cause the farm to either not plant new fields of alfalfa hay or rip out existing fields of alfalfa hay, you start having significant costs to these water interruptions. So as you can see, starting at about a 20% shortfall, going up to 50 or 60% shortfall, you go from about $60 to about $300 an acre foot. And you can see that for the alfalfa hay farm, the cost of interruptions increases the more consecutive years these interruptions are experienced. This is because as the length of these interruptions increases, the alfalfa hay farm rips out more fields of alfalfa, which on the normal rotation cycle the planted fields of alfalfa could yield several years of additional profits before they have to be fallowed. This table presents the total cost of an alfalfa hay farm not receiving 10% of its expected water deliveries due to an unanticipated supply reduction. And you can see that, if these supply reductions take place during drought conditions where there's already a shortfall, and if they last for several consecutive years, the cost of a 10% reduction can be substantial in terms of the net present value of profits. This table shows the sensitivity of the model's predictions about the per acre foot value of water to a change in the sale price of alfalfa hay. As you can see, the model's predictions are very sensitive to the sale price of alfalfa hay. As you'd expect, as the sale price increases and alfalfa hay is more profitable, the value of an acre foot of water correspondingly increases. Next, we want to ask the question of whether or not our model's predictions about the value of an acre foot of water are reasonable. So we looked in a number of different sources to try to assess this question. First, looking at Water Strategist, which is the leading trade publication in the US on water markets. While they don't have a lot of data on Nevada, on leases in Nevada, they find that the average lease price, the average cost to lease an acre foot of water for a year, is about $165 across the western US. Westwater Research performed a recent study where they used data from on water use and data from the USDA Ag Census to demonstrate the productivity of irrigation water. And they find that irrigation water has a value of about $166 per acre foot averaged over the entire state. So our report, our values of acre foot of water are higher than these estimates. There's good reason to think that the value of an acre foot of water is going to be higher than the value on a lease market for an unanticipated reduction, because we're considering in the model an operation that's set up to use a fixed amount of water, their expected deliveries, and then in a given year does not receive their expected deliveries due to conflict or due to some other reason. And in those cases, the costs are going to be higher than how much the same operation would actually go out and be willing to pay for additional water on the lease market. Another important caveat is that we have prices that diverge from these estimates only in years where the supply interruption occurs concurrently with a drought, and is likely the case in Nevada and on these other western states, that there's not going to be a very robust water lease market in those circumstances in drought years, and the price is likely to be much higher than these average prices that these studies are reporting for non-drought conditions. So, we think our figures can seem reasonable, even though they are a little bit higher than what these other sources have reported. We've also compared our estimates with data on permanent water rights sales in the Humboldt River Basin. There's a huge variation in the price of permanent water sales over the period where we have data from 2006 to 2019. So these numbers correspond to an annualized value, so the value of an acre foot for 1 year, ranging from as low as $26 to as high as $340 per acre foot. So this doesn't tell us a tremendous amount, but it does say that our dollar figures for the per acre foot value of water are in line, at least, with the permanent water rights sales in the Humboldt River Basin. Of course, the permanent water rights sales are, do not guarantee that you're going to receive the amount of water in your duty every year. So it's reasonable to think that for a lot of these water rights, particularly more junior water rights, that the value of the water right would be less than the annual value, the compounded annual value of that water for the operation in terms of increased profits. So one of the things that became clear in the process of putting these two models together is that we need to get more stakeholder input to make sure the models are really give an accurate picture of ranching alfalfa hay operations and the variety of different alfalfa ranch and farm operations in the Humboldt River region before this kind of work can be included in a credible way in a management process. One dimension that we're kind of particularly interested to look at is there's kind of big differences between ranches and how ranches use public land in the Humboldt River region. So we of course have a model where the ranch has access to the public land allotment over the summer, and we kind of want to make potentially a second model where the ranch uses public land for winter grazing. So that's one dimension where we definitely want to change, but we envision another round of stakeholder input and potentially multiple models that capture the variety of different operations in the Humboldt River region. We're also considering extensions related to seasonality of water flows and timing, and then when the unanticipated supply reduction occurs, which part of the growing season. Also looking at how the cost of these interruptions differ depending on water right holders of different seniority. I'd like to thank you for listening to my talk, and I'd like to thank the Nevada Water Resources Association for putting on this conference. Again, if you have any questions about this presentation, please come to the live question and answer session, which is going to be held on Monday, January 25th at 10:10 a.m. And again, I encourage you all to listen to the other two presentations in this panel by John Benedict and Kip Allender. And again, I'd like to acknowledge the support for this work from the Nevada Division of Water Resources. I'd also like to acknowledge the support from Nevada Cooperative Extension, where I have an appointment, and also the Nevada Ag Experiment Station, which was able to support Kim Rollins' work on this project.